and fx0 is still greater than fx0 plus the delta, of sigma, because of the assumption we want to find the minimum, right? So the minimum must lie to the right of x0. So the minimum should be here from fx0 to the right, not to the left. Yeah, so that means the sigma is chosen to be positive. You choose this one, not the minus, because you want to go from fx0 to the right. Okay, if the inequality are reversed, sorry, then it's the other way around. Yeah, choose the negative. What is it? In so this one fxo minus sigma less than equal to then fxo, and fxo is less than equal to fxo plus sigma, then you want to go to the left. We're gonna use this one because this is the smallest. Okay, this is what it means. Now the second if, it should not be, it should be here. If this is not the condition or the reverse of this, but this one. Fxo is actually in between these two. Fxo is in between these two. That means the minimum has been bracketed between. That means it's between these two. So it's correct. This is what you need to want to, this is what you want to find. Okay. All right. I ran out of the time, so I'm gonna share you the other one. Okay. Hang on. Where is it to chat? I hope I can still have time. Okay, you can join. And screen 2 is this one. Okay. Can you see the screen 2 now? Okay, let's continue. Yeah. The others should join soon, yeah. They haven't, please remind them. Okay. There you go. Someone is joining again, right? So here, let's continue. Here. So here, the last one, the remaining case where if fx0 is actually greater than fx minus delta and fx plus delta, so this is actually higher value. That means it's not convex anymore. It's probably not unimodal or not convex. Yeah, it means you are in the wrong place. You should change somewhere or check again. This is not convex. There is no minimum, only maximum probably, or no, or um, saddle point. Okay, here. Okay, let's do the example. Yeah, bonding phase. So here we have this problem. This is the equation. Fx is 100 minus x squared, a power of 2. And you're given the starting point as x0 is 30. And then you're also given a step size as 5. Now we are trying to find the good bounding phase between A and B. What is A and what is B, for example? Yeah. Here. So now the sign of sigma is determined by comparing this. You just need to put, okay, XO is 30, 30. What is F30? 4,900. If FXO plus delta, which is 35, F35 is 4,200-ish. And if it's FXO minus delta, it becomes F25, is actually increasing. Yeah. 5,600-ish. So we can see that the lowest is this, yeah, F35. Middle is F30. And the highest is F25. From this, we can see that we want to find the lowest point. So we should not go to the left. We want to go to the right. Yeah. That means we will choose the sigma that is positive. We're going to choose this one, not this one. Yeah, we want to go to the lower point. That means the minimum point fx star must be greater than 30. So if this is 30, fx x0 is 30, that means the x star must be greater than 30 because the greater it is, the lower it is the value. See, 35 is 4,200. Lower. If it's this one is higher. So that's x1 now, the updated x1 is equal to x0 plus delta, which is 35. How can we get this formula from here? X1 is x0 plus delta. Where is the 2? Remember, k is 0. In this case, k is 0. This is xk. This is xk plus 1. So k is 0. This is x0. This is x1. Yeah, k plus 1. How about this? 2 to the power of 0 is 1. That's why we only have this sigma. So x1 is equal to x0 plus sigma. Okay, that's why we get this x1. We choose x1 to be 35 because of that formula. Okay, and then continue. Now we need to find x2. Right? We already have x1, which is 35. Now, how about x2? Yeah, x2 is what? x1 plus 2 to the power of k multiplied with sigma. Yeah. What is x2? 35 plus 2 multiplied with sigma. 2 multiplied with 5. 20, 35 plus 10 is 45. Yeah. And we plug into the f. We got 3,000 now. Lower than fx1. Fx1 was, this is fx1, was, what is it? 4,200. Here is 3,000. So lower. It's good. We're progressing. Okay. So we need to continue. And therefore, x star is greater than 35. Okay. Again, how can we get this x2 formula from here? X2. X2 is equal to x1. That means the k is 1. Plus 2 the power of 1 multiplied with sigma. Okay. X2 equal to x1 plus 2 multiplied with sigma. Okay. Here. And get lower. So it's good. Now, again, x star is greater than 35. What is x3 after we know x2? x3 is x2 plus 2 the power of 2 sigma. How can we get this formula again? X3 is equal to x2, so the k now is 2. K is 2. So x3, which is from k plus 1, x3 equal to x2 plus 2 power of 2 multiplied with sigma. Okay, x3 is equal to x2 plus 2 square multiplied with sigma. Here. Yeah, x3. And then putting inside what is x2, what is sigma, we get 65. And put 65, x3, 65 into the f. We got 1,200, even less. It's good. We are getting better now. We're getting more minimum. Yeah. And then continue. Now x star is greater than 45. We now define x4. Yeah, which is in this with the formula, we get x4 is 105. Putting into the f, we get f. Oh, now f is 25, even less than this. Good, great. We're getting better now. Yeah, you want to find the minimum, right? And then with x5, could continue the same way. We get x5 185 and f 185 is 7,000 now. We are increasing already now. That means fx star should be less than 185. Sorry, x star should be less than 185 because 185, if we put it, is increasing. We had 25 before. Now it suddenly becomes 7,000. So definitely don't go toward that. Okay, x star must be less than this. So now we can put the bracket into a correct one. Yeah. So if x star is definitely less than 185, because we want to be less than this, but it's also more than 65, right? Based on this, it's more greater than 65, but less than 185. We can now put the bracket. So x star is between this. Or this is A, this is B in the graph. Remember the graph between A and B? This is A, this is B. There you go. Up to this point, any question? Yeah, which one? Oh yeah, yeah. This is why it must go positive because yeah, when we plug in XO is 34,900, F35 is 4,200, 25 is 5,000. Yeah. So this is 5,600. This is 4,900. This is 4,200. Okay. So this is biggest, lower a bit, lower again. If we want to find the minimum point, where should we search? Should we go to the right or to the left? If you go to the left, you're gonna have bigger value. This is already 5,000. Yeah. If you go to the right, it's getting less from 5,000 to 4,900 and getting less again from 4,900 to the 4,200. So you want to go to the right. And what does it mean by going to the right? You want to go to the positive, positive, not the negative. There you go. Do you think? Do you understand now? Okay. So based on this, it could be different. Could be you will need to go to the left, probably. Based on this though, chosen positive or negative or in between, or is actually not convex at all. It's not unimodal. You're in the wrong part of the function. Yeah, here. So you be mindful when to choose the positive, when to choose the negative, and when to stay there, remain there, or when to check the function. It's not unimodal, it's not convex at all. Okay. Yeah. Another question? Yes. Yes, here. Okay, minimizing fx. All right. Any question? Other question? Okay. Right, right. Let me check. Try Okay, we still have time here. We have some time. Is it clear? To make the A and B now. After that, we have this interval halving and golden search for the interval refinement. So after you have the A and B, and to make it small. Yeah, small enough, hopefully you can find the X star. But if it's too difficult, at least it's very small. Compared to A and B like this, it's going to be like this. Okay, if you see my video, you can see my hand is moving. Okay, there. Right. So let's discuss about this interval halving. Yeah, you want to refine now. And we have the algorithm. Yeah. Um, Basically, interval halving is you just cut into halves. This interval, you cut in half. And those half cutted interval, you cut in half again. You just move from cutting half and half and half and so on until you make it smaller, 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 but cut in half. Yeah. Delete exactly one half or half, yeah, after interval. Yeah. It means by cut, after you have this big, you cut in half. The other one you eliminate because it's worse or not minimize, getting greater. That means you want to eliminate the other thing. Similar to the balding face, but this one is cutting. And this is the algorithm. Yeah. Um, um, I think you already learned about algorithm class, probably, right? In the last year. This one example. Yeah. Uh, so first step, let xm, m is the middle point, is half between A and B. Okay, you have A and B, cut it half. That's in the exact half point is xm. And the region is L is B minus A. Then compute fxm. Check in the exact half, what is fxm? And then second step, set x1 to be A plus 1/4 of L and x2 to be B minus 1/4 of L. So it's kind of like you already cut this in half and then cut it again to find x1 and to find x2. Yeah, in the whiteboard I can show you the picture, but here it don't exactly show. Yeah, but after you have A and B cut in half, and you want to find the half of those halves cut it and find x1 and x2. Yeah. So if you have the left side A and the most right this side is B, x1 is kind of a quarter from A. And another quarter is xm, and then another a quarter to the right is x2, and then another quarter is B. Can you imagine that? Yeah. So now we have point x1, of course, A, x1, xm, and x2, which are equally spaced or 1/4 or a quarter. Yeah. Compute fx1 and x2. And then you go to this step 3. Yeah. Compare fx1 first with and fxm. See which one is lower. If fx1 is lower than fxm, that means you want to be in the lower side. That means drop the interval xm and b. That means above xm, you need to eliminate it. Above xm, you need to eliminate it or drop the interval. By setting, previously it was b, now b, no, now xm become b. This is the new b. The old b was a bigger number. Now the new b is equal to your xm. Yeah, the midpoint. Yeah, and now the midpoint previously was xm, now become x1. So now the new xm is equal to x1. So set xm equal to x1 and set b equal to xm. And then go to the step 5. check L, B minus A. If you think it's small enough based on your goal, then finish. Yeah, otherwise return to step 2. Again, doing it again, the same way. Yeah, go repeat again. But if fx1 is greater than fxm, yeah, that means you're not in the correct half side. You need to go to the other side, which is go to step 4, the between xm and x2. So now you're comparing fx2 and fxm. Check if fx2 is less than fxm, that means you want to go to the fx2. You want to go to the right side of xm or fx2. You drop the interval a at xm, which means between a and xm is bigger. You want to go lower, so you want to go to the right of xm. Don't want to go to the left side. The left side of xm is interval a to xm. Yeah, while the right side of xm is interval xm to b. To b. Yeah. So you want to go to the right. Since the midpoint of the interval will now be x2, set xm equal to 2 and go to step 5 again. Yeah. But if fx2 is greater, so fx1 is greater and fx2 is also greater than fxm, there you go. That means fxm is both, no, fxm is lower than both fx1 and fx2. That means that might be the optimal, might be. But you want to drop the interval, you want to make the interval from here to smaller. Okay. From A to B into x1 and to x2. A to B become x1 to x2. You make the interval closer to each other. Okay? But the midpoint is still xm. And continue to step 5. Repeat. Okay. I know that this might be much easier with an example. So let's go on to the example here. Note before the example, at each stage of the algorithm, exact half the length of the search interval is deleted. Yeah. And then the midpoint of subsequent interval is always equal to one of the previous tile point, x1, x2, or xm. Hence, at most, two functional evaluation are necessary at each subsequent step. The evaluation means finding out the fx, checking. Yeah. Based on the x1, x2, and xm. And after n function evaluation, finding fx and basically iteration, the initial search interval will be reduced to this. If you want to know how fast it's reduced, from here, how fast it's going to reduce, the speed of the reduction is 1/2 the power of n-half. Okay, if someone asks you about the speed, or into what? Yeah, into what? How it's the size. Okay, let's go to the example. Okay, so let's see this. We have this fx, same as before, probably, yeah. 100 minus x to the power of 2. And we have the interval from the bounding phase. We got 60 to 150 in this example. So A is 60 and B is 150, which means the L is B minus A, or the length of the bound is 690, so 90. The length is 90. Let's find the middle point, xm, which is half of 60 plus 50, 150, or 105. This is between 60 and 150, exactly in the middle. Okay, is this one. Okay, and now let's go then to the interval halving. Search, we know xm. What is x1? Let's set step 2. X1 is A plus a quarter of L. X2 is B minus a quarter of L. X1 is A plus a quarter of L, which is 60 plus 90 divided by 4. We got this number, 82.5. X2 is B minus a quarter of L, or 150 minus 90 by divided by 4. We got this. Now we have how many points? We have actually 5 points. We have A, 60, and then we increase into X1, which is 82.5. We increase again, we go to the right, XM exactly in the middle, 105, and we keep going to the right into X2, 127.5, and at last we go keep to the right until we get the max B 150. Okay, if I draw in the picture, it's like that. Yeah, yeah. So now you plug in like this. Maybe here, this one. FX21 and then X2 plug in. FX1 is 306, FX2 is 756. Okay, we have this. So let's see. FX1, sorry. FX1. FX1, see, is it greater or not than FXM? FX1 is 300. FXM is 105. So FX1 is greater than FXM, which is 25. Again, this is FX1, this is FXM. So FX1 is greater than FXM. 300 is much greater than 25. That means we have this condition. Not this, but this. Then what's the algorithm? Go to step 4. Now let's compare now FX2 and XM. What's the comparison? FX2 is this one. FX2 is 756. FX1, sorry, FXM is 25. And 700 is much greater than 25. So this is this condition. FX2 is greater than FXM. FX2 is greater than FXM. Okay, so we are here now. That means drop the interval A and X1 and X2 to B. And the new A now is X1, the new B become X2. The midpoint still the same. Drop the interval between 60 to 82.5 and drop the interval between 127.5 to 150. Yeah. Now the new A is not 60 anymore, but 82.5. The new B is not 150, but 127.5. So the interval is between what? 82.5 to 127.5. The interval. This is A, new B. And what does it mean by this? The length. The L, previous L was 90 from 150 minus 60. The previous L. The new L is 82.5, sorry, 127.5 minus 82.5. It's 45. So it's not like this. It was like this, now become like this. Okay. This stage. Any question? Everything clear in this stage? Okay, hope it's clear, yeah? Okay, now we want to continue. We have changed the interval between A and B from 60 to 150 to become 82.5 to 127. Let's do the another stage. The new A is this, the new B is this. So the XM is still the same. Let's L is 45. Let's calculate again. X1 based on the formula is A plus 1/4 of L. A plus 45 divided by 4. X2 is B minus 45 divided by 4. This is x1. This is the new x1. This is the new x2. And again, using the algorithm again, yeah. Check, compare fx1 and xm. Okay, let's see. fx1 is 39, fxm is 25. Oh, it's greater. fx1 is greater. We are in this condition. In the stage 2, we are in this condition. Okay. Step 4 then. Let's compare fx2 with fxm. fx2 is 100, sorry, 264. fxm is 25. Still greater. So we are in here again. We are in here again. So we'll reduce the interval. Yeah, the new f, so the new a is not from 82 become 93. The new b from 127 become 116. Okay. And then with the same stage 3, we have new a, new b, new x, still same xm. L is this, x1 is this, x2 is this, yeah. Um, based on the formula like this, yeah, just make it faster. Now let's check based on the algorithm, what is fx1 compared to fxm? X1 is 0.39 now. fxm is 25 now. We are in different condition. Now we are not in here, but we are in this condition. fx1 is less than fxm. We are not in here. So we won't go to step 4. We will go here. Drop the interval x and b by setting b equal to xm. Then the midpoint of the new search will now be x1, and hence xm is equal to x1. So we see that, hey, this is lower now. We like this part. We don't like this part. So the interval now, we delete 105 above. Before the interval was until 116. Now we make the new b become 105. Okay, the new interval starting from still the same a, 93.7, but the new b now is 105. Okay, the midpoint is not 105 anymore because this become b. So we need to find the midpoint is between these two. Okay, this plus this divided by 2, we got 99.30675, which is the same as x. Yeah, apparently same as this one. Yeah. So with this 3 stage of iteration, you can say, first we have L of 90. First one, we have L of 90 between 60 to 150. The length is 90 between A and B. With 3 stage, it's been reduced into 11 only. Yeah, 11 only. 11 basically from this minus this, or this multiplied with half the power of 3. Yeah, this is basically this minus this or this, and this formula is from this. Okay, if you don't want to do it, you can just calculate this and want to see how many stages do you need to do it. Yeah, and then actually do it so you can actually know what's the A and B. Where's the actually A and B, A and B. But you will know the L before actually doing it from this formula. Yeah, and see if it's enough or not. If this is okay, it's good enough. Let's just guess the X star is between this, it's fine. But if, okay, that's not enough, we want to have a L5 or less than 5, then you need to do until it's several stage, one statement, yeah. There. Any question to decide? Okay. that clear?
Yes, Pak.
Okay. This, I'm gonna put this for next time. I don't think it's good if the time is too close. Let's discuss it next class. Yeah. So this is the of search space. Okay, and close this. And since now everyone has submitted, I want to show you the answer. Yeah. There you go. There you go. Yeah. So from last week, yeah, with this example, yeah, then this is the answer. So we have this max fx, and this is the equation. When we know that we are given the interval, then first step is we need to find the necessary condition, which just the first derivative of fx and equal to 0. So first derivative of fx is equal to 0. We got x is minus 1 or x is equal to 3 to get 0. So these are the stationary points. This is the space. These are the spatial point. Yeah, could be minimum, could be maximum, could be saddle point, but this spatial point. And then we continue with this second derivative, yeah, of this function. We have now minus 6x plus 6, yeah, to find the local min and max. And then if we put the the second derivative x as equal to minus 1, we get 12. And then if we put the x equal to 3, we have minus 12. The same. What was the question again? Yeah, we get the stationary point, and then we got the local minimum maximum with the sufficient condition. Which one is the minimum? Which one is the maximum? Yeah, if x, the second derivative positive is minimum. If the second derivative is negative 12, that means maximum. So we got this number B. Then convexity, concavity. There. The second derivative, if we put it equal to 0, we'll get x equal to 1. Yeah. Now, we want to see if x is equal to 1, what's going to be to the left and what's going to be to the right. When x is less than 1, the fx, when we plug it in, the fx will be greater than 0. That means it's going to be convex. If it's concave, then if x greater than 1, we plug it into the fx, and second derivative is less than 0, it becomes concave. So in this case, what do you think? When x is less than 1, for example, when x is 0, for example, yeah, 0 is less than 1. If x is 0, that means the second derivative is going to be greater than 0 because it's going to be 6. That means less than 1 is going to be convex. How about if x greater than 1? X is 2, for example. Put 2 in here. 2 multiplied with minus x plus 6 become what? Minus 6. Minus 6 is less than 0. That means if it's greater than 1, it is concave. So, there you go. Why I have the x-axis? Yeah, there you go. Oh, this x-axis is, can I remove this? Um, there you go. Yeah, so the graph, if to the right of x equal to 1, it's going to increase and then decrease, become concave. And left of 1 is going to be decrease and then increase. So this is the if you draw it, yeah. So which part is convex, which part is concave? And then the question again is increasing or decrease indication. You know now where's the convex, where's concave? How can we know when it will increase, when it will decrease from left to right? After you know which one is convex, which one is concave, and you also know the stationary point, the special point. The special point is x minus 1 and x equal to 3. So x minus 1 is here, x3 is here. The special point, it means it could be the maximum, could be minimum. Since x minus 1 is in the convex area, that means the x minus 1 must be the minimum point. And since the x equal to 3 is in the concave area, and x equal to 3 is the spatial point, it means that's the maximum point. So from less than minus 1, it's going to be decrease, or in this case was the interval. Okay, from minus 2 to 4. So from minus 2 to minus 1 is decrease, and then reach minus 1, x equal to minus 1, which is the minimum point. And then from minus 1 to, what is it again? To 3, this is wrong, yeah, should be minus 1 to 3, is increasing. Because from convex, it keep increasing until concave. And then we reach x equal to 3, which is the spatial point, and concave, it also means the maximum point. And if we keep continuing to the right, it's going